Welcome to video number 2 in the series of 3 talking about calorimeters. And in the last video, we saw how we can use calorimeter to come up with the specific heat of a solid like a metal. This time, we're going to look at how we can find the heat of reaction using a standard calorimeter. So we've been talking about heat of reaction, and it's denoted with the variable Q. And it's a quantity dependent upon mass, hence CumSat, Q equals M times C delta T. That's why I say CumSat or CumCat. But we also can define heat in the terms of enthalpy, which is also going to be symbolized by delta H, and that's going to be a molar quantity. And so the change in enthalpy, or the change in heat in a system, is going to be the amount of heat of the reaction divided by the number of moles present when the reaction occurred. So I'm going to give you a moment to pause and write that small little equation down. And then what I'm going to do is I'm going to show you how this works. Okay, so let's see how this works here. This is going to be one of those really great questions that we're going to tie in some solution stoichiometry. We're going to tie in some balancing equations and limiting reactants, all with this calorimeter type of problem here. So when a 1.00 liter of a 1.00 mole per liter barium nitrate solution at 25 degrees Celsius is mixed with a 1.00 liter of a 0.500 mole per liter sodium sulfate solution at 25 degrees Celsius, white barium sulfate is formed. So that's the product we want. And the temperature increases to 28.1 degrees Celsius. So we're going to assume the specific heat is basically that of water, and that the density is basically that of water. We're going to find the enthalpy of the solution. So step 1, whenever I'm doing these problems, I first say, hey, a reaction occurred. I probably need a balanced chemical equation. So barium nitrate, I pull out my periodic table. Barium is Ba. Nitrate polyatomic table is NO3. This has a -1. This has a +2. So I've got BaNO32 plus sodium sulfate, and I gave you that formula, so I don't have to go through and do the charges. And it's a double replacement reaction where I'm going to create BaSO4, and the leftovers are going to be the sodium that hits with the nitrate here. So I'm going to do plus NaNO3. So now I'm going to go back and balance. I need two NO3s. So I'm going to throw 2 in front here. And that coincidentally balances out my sodiums. So step 1, balance chemical equation. Step 2, we're going to do some solution stoichiometry. So I'm going to go down here and I'm going to say that I am going to decrease the size of my line here real fast. Makes it look a little bit nicer. Okay, if that actually worked, probably not, but we'll try it. Don't think it did. All right, so I've got a concentration, a volume, and a number of moles for both BaNO3 and Na2SO4. I need to figure out, first of all, how many moles of each one of these reacted, and second of all, which one of these limited the amount of barium sulfate that's going to be created. So my barium nitrate had a concentration of 1.00 moles per liter. My volume is going to be 1.00 liters. And remember this little equation here, CV equals N. So I had 1.00 moles of the barium nitrate that reacted here. I'm using my balanced equation as a structure for my table. So sodium sulfate, I had 0.500 moles per liter of that. Same volume of the solution here. And CV equals N. I'll end up with 0.500 moles of my sodium sulfate. Now, we're lucky that the two reactants and the product is in a 1:1:1 ratio. Sodium nitrate, we don't really care about. It has a coefficient of 2 out front, but that's in excess and in solution, so that goes away. So that means the smaller number of moles in my reactants, it's going to limit the amount of barium sulfate formed. So I'm only going to form 0.500 moles of the barium sulfate. So there was step 2, figuring out my number of moles and what number of moles limited the amount of product I could make. So I'm going to set this aside for the time being, and I'm going to come back to it. I need the number of moles a little bit later on. It's time now to get the heat of reaction. So here comes CumeSat. And we assume that all of these chemicals were dissolved in water. So we are actually figuring the heat of the water, and the heat that was added to the water is going to be equal and opposite to the heat that was lost by the reactants. We also know that since this is mostly water, and the density of water is 1 gram per milliliter, and I've got 2 liters worth of solution here, so I've got 2,000 milliliters of solution here. Therefore, I've got 2,000 grams of solution. And once again, that's because this is 1,000 milliliters of barium nitrate. This is 1,000 milliliters of sodium sulfate. So that's basically 1,000 grams, or 1,000 milliliters plus 1,000 milliliters is 2,000 milliliters, which is the same as 2,000 grams. Essentially, we have mostly all water, so we're going to use 4.18. And my change in temperature, I went to a high temperature of 28.1 from an initial temperature of 25.0. I do want to address sig figs here, because I need to subtract these two first. And when I subtract, I round to the lowest number of decimal points, which is 1. So my change in temperature is 3.1, which, look at that, it all of a sudden changed all of my measurements now to 2 sig figs. This technically has 3 sig figs because it's 2.00 times 10 to the third, because I've got 1.00 for 3 sig figs here. So I'm now down to 2 sig figs. So I've got 2,000, which I'm going to remember was 3 sig figs, but it doesn't matter anymore. Grams, 4.18 joules per gram degrees Celsius times 3.1. I'm going to throw all of that into my calculator, and I'm going to get 26,000 joules. And a joule is a very small measurement of energy, so we usually go to kilojoules, 26 kilojoules. And it still has 2 sig figs. Last step, we found how much heat was released for 2,000 grams, and we know this 2,000 grams created 0.500 moles of product. So for 0.500 moles of barium sulfate created, I released, and I should put a negative sign here because I'm releasing it, 0.500 or 26 kilojoules of heat for every 0.500 moles. And so this reaction released 52 kilojoules of heat per mole. And that is going to be my enthalpy. Negative 52 kilojoules per mole. All right, so there was a lot to unpack there. We first had to do my balanced equation. We needed to figure out the number of moles reacting. We needed to figure out the limiting reactant, which limited the amount of barium sulfate that we created. We then found out how much heat was released from the reaction from the amount of heat gained by the water. Then we took that and divided by the number of moles to get my enthalpy. So you're going to have some practice to do with that, of course. And this was part 2 video. Hopefully you enjoyed it.